Okay, here we are. This final week of the course on analytical techniques for wave phenomena, we will address some problems in the time domain, that is transient problems, and they will give us the chance of introducing further applications of complex function theory, as you will see today, and also in the last lesson of next Thursday. Let us first introduce the concept of transient waves and transient electromagnetics in particular. Why are we interested in studying the transient response in general inhomogeneous media configurations, including in particular layered media, which were the subject of the examples we studied last week in the time harmonic regime? Well, one advantage of using transient signals is that in this way you can acquire in a very short time data on a large bandwidth that otherwise would be much longer to take if you proceeded directly in the frequency domain. On the other hand, the very transient nature of the time domain signal allows you also to separate different events, wave events, simply because they occur at different times. So if you window your observation interval by a procedure known as time gating, then you are able to observe different wave phenomena which are related maybe to different aspects of the object you wish to study, for example, to interfaces or discontinuities and so on. So for this reason, there are many applications, in particular many measurements that are intrinsically transient in nature, for example, radar, more generally sounding, wave sounding of inhomogeneous media, and also electromagnetic or wave diagnostics like tomograms, okay, used in medicine. As concerns in particular electromagnetic transients, well, these generally require quite large bandwidths. That is because the electromagnetic waves travel very fast. They are the object that travel faster in our world. In particular, consider that electromagnetic waves travel 30 centimeters in 1 nanosecond in vacuum. And so if you wish to observe structures and to a detail of the order of 30 centimeters, then you should employ a 1 nanosecond pulse. Otherwise, you would lose your resolving power. And this implies in turn a bandwidth of the order of the inverse of this time, so 1 gigahertz. So there are large bandwidths. And now the signal-to-noise ratio in transient measurements is typically smaller than for time harmonic measurements for this reason. One way to overcome this is to use slower waves, and this is why acoustic measurements are quite popular. In that case, the velocity of the wave is much slower, and therefore the wavelength is in turn shorter for a given frequency, and transient measurements can be achieved essentially with less bandwidth and therefore less noise. Also, of course, acoustic waves are certainly not harmful, and this is why they're used in diagnostics, echographies, and so on. Okay, let us see some basic facts about transients, starting with perhaps the most basic thing that we need to take into account, that is the so-called causality. Causality is simply expressed by noting that physical grounds require that the time domain response of any physical structure cannot exist, so it must be zero until after an exciting signal is applied. That is, any physical system cannot react before you apply some signal to excite it. So in terms of a general input-output schematization, like the one showing at the center of the slide, if x is the input signal as a function of time and y is the output signal, then if you assume that the input excitation x is 0 before some particular instant, in this example, the instant equal to 0, so the origin of this Cartesian plane, then you cannot expect expect an output to exist before the same instant. So you can exclude by causality an output response like the one depicted here at the bottom right of this slide. But there is even more. Actually, in any physical system, if you observe your output at some finite non-zero distance from the excitation, then you should take also into account that any signal travels with a finite velocity. So therefore, not only the output will be zero until the time when the signal is applied, the excitation is applied, but in addition, you should also allow for such signal to propagate from the source to the observation point. So there is a delay due to the finite propagation speed, okay? And this propagation speed actually depends on the wave you're employing, but take into account that there is a profound implication of special relativity, which postulates that no signal velocity can be larger than the velocity of light in free space. And in particular, if your signal could move faster than this speed of light in free space, then this would violate causality. That is because if it would allow then a signal to be sent across what they call space-like intervals in special relativity. And in turn, this means that there is at least one inertial observer for which the signal would travel backward in time, which is, of course, non-physical. So if special relativity holds, and all the clues, the experimental data we have collected so far indicate that special relativity is valid, then if you don't want to violate causality, then you should enforce that any physical speed of your signals be lower than the speed of light in free space, in vacuum. Now, causality also occurs in constitutive relations because those relations can be thought as an input-output relation in which there is the input field, which could be called also the cause, for example, the electric field or the magnetic field, and the output is instead the response of the medium, which could be described by, for instance, the electric induction, the magnetic induction, and the conduction currents. And those could be named the effects, okay? So there is an input-output relation, and if your medium is in particular linear and stationary, and also for simplicity, let us assume that it is homogeneous and isotropic so that it is described in simple scalar terms, then for a medium which is temporally but not spatially dispersive, the input-output relation is in the form of a simple superposition integral, which is in particular a convolution integral. As you can see here, the input or the cause, the excitation, that is the electric field inside the integral, produces the effect, that is the electric induction at the left-hand side. And we have an integral kernel, which is the permittivity, epsilon. And as you can see, this is a typical convolution integral, okay, which can be also cast in this alternative form in which the argument of the electric field is t minus tau instead of being the argument of epsilon. Those are equivalent. And the important thing, of course, is that if you now evaluate the Fourier transforms of this relation, then an elementary property of the Fourier transforms tells us that the convolution product becomes a simple algebraic product. So now, in the frequency domain, the relation between the input and output is given by a simple multiplication which involves this complex scalar function epsilon of the radiant frequency omega. Now, of course, epsilon as a function of omega is the Fourier transform of epsilon as a function of its temporal argument. And so, conversely, epsilon as in the time domain is given by the inverse Fourier transform, that is 1 over 2 pi, the integration over the real axis of epsilon of omega times the Fourier exponential. Now, causality in this framework is equivalent to requiring that the kernel of this convolution, that is the permittivity, be zero when time is negative, so before any excitation is applied. Let us explore the consequences of causality in this context. One first fundamental consequence is that if you now evaluate the frequency domain permittivity, then this results in a holomorphic function of the radiant frequency omega, at least in the lower half plane, that is in the portion of the complex omega plane where the imaginary part of omega is negative. And this is shown quite readily. By definition, the Fourier transform of epsilon in time domain is given by this integral here, where now you can see the Fourier exponential with a minus sign, because now we are evaluating a direct Fourier transform. Now, if the epsilon in time domain is causal, this means that it is 0 for negative times, so you can limit your integration interval from 0 to infinity, okay? Now, in turn, this implies that if omega has a negative imaginary part, and since we are now considering positive times, then the integrand in this integral decays exponentially when time tends to plus infinity. And so the integrand is integrable on the positive real axis. Then consider an arbitrary closed curve, gamma, as the one shown in this picture here, that lies entirely in the lower half plane of the complex omega plane, okay? And let us evaluate the integral along this closed curve gamma of epsilon in the frequency domain. So this is a complex integral, a contour integral in the complex omega plane. Let us introduce the definition of epsilon of omega as a Fourier transform. So we have now a double integral. The external one is a complex contour integral. The internal one is a real integral, the Fourier integral. Now, since the inner integrand is integrable, as we saw, then we can exchange those two integrations by means of Fubini's theorem. And so we let the temporal integral be the exterior one now. And what remains in the inside integral is that you need only to integrate the Fourier exponential along the closed curve gamma. However, as we know very well, the exponential is a holomorphic function in the entire plane. It's an entire function. So by Cauchy theorem, its integral along any closed curve must be equal to 0. And in turn, this means that the integral at the left-hand side, then this must be equal to 0. So we have discovered that the epsilon function in the frequency domain, epsilon of omega, is characterized by having its integrals along any closed curve in the lower half plane be equal to 0. But we know that this is in turn equivalent to saying that this function is holomorphic in the lower half plane, because we know that Morera's theorem holds. I remind you that Morera's theorem, as we saw in the second lesson of this course, is a converse of Cauchy theorem. Cauchy theorem tells us that if a function is holomorphic, then its integral along any closed curve contained in the domain of holomorphy, which does not wind around any exterior point, is equal to 0. Morera's theorem tells us the converse. So if you have a continuous function whose integral along any closed curve is 0 inside its domain of definition, then this function must be holomorphic. So we have discovered, we have proved actually, that in the frequency domain, the permittivity is a holomorphic function of the radiant frequency omega. But this has now a bunch of consequences, because we can now use all the theorems and properties that characterize holomorphic functions. And in particular, we can make use of Cauchy integral formula. Consider, for example, an arbitrary point omega in the lower half plane, like this one, the picture. And let us enclose this point inside the contour in green, which is made from a segment, a horizontal segment, C1, lying on the real omega axis. Here we are in the complex omega prime plane, so we can call the fixed point here omega. The other part of the contour is this half circular CR contour, which goes in the clockwise direction below. Here you can see the parametric representations of C1 and CR, where C1 is parameterized by x prime that goes from minus capital R to plus capital R, and R is a number that we will ultimately let to infinity, whereas CR is parameterized by the angle psi, which goes from minus pi to 0, okay, or better from 0 to minus pi, according to the clockwise direction. So if we now use Cauchy integral formula, we are able to express the permittivity at the point omega as a line integral, a contour integral of the permittivity divided by omega prime minus omega, the integration being performed with respect to omega prime, okay? And then there is, of course, the factor minus 1 over 2 pi j, in which the minus is due to the clockwise direction in which we are integrating. Now, we will let the radius r tend to infinity, and in this limit, we would desire that the contribution of the half circle be negligible. However, this is not the case, and the reason is that inside our time domain permittivity, there is an instantaneous response. Consider that our electric induction, that is the effect, can be written in general as the induction that would be present in vacuum, which is simply the electric field multiplied by epsilon 0, a real constant, plus a polarization density, which is expressed in terms of the electric field and the electric susceptibility, chi. Now, this means that the permittivity in time domain is given by the sum of two addends. The red one is the so-called instantaneous response, and this is what would exist in a vacuum, the only term that would exist in a vacuum. And this contains a Dirac delta. That's why it is called instantaneous response, okay? If you imagine to introduce the Dirac delta inside the convolution integral, then what you obtain is directly the electric field at the same time at which you evaluate the effect, okay? The remaining part is the so-called delayed response. That is due to the physical phenomenon of polarization of the medium, okay? And this is described by this chi function here. Now, on physical grounds, this function should be an ordinary integrable function, and therefore, by the Riemann-Lebesgue lemma, its Fourier transform should be infinitesimal as omega tends to infinity. However, because there is also the instantaneous response, if you calculate the Fourier transform of the Dirac delta, you get the constant 1, and therefore, when omega tends to infinity, the permittivity in the frequency domain does not tend to 0, but it tends to epsilon 0, which is a non-zero constant. There is even more, and there are permittivity models which are valid in some restricted frequency range, in which you can have an additional instantaneous contribution. And this means that, in general, the permittivity as a function of omega will tend to some constant when omega tends to infinity, which may be different from the permittivity of vacuum. And we will call this constant epsilon infinity, to remind us that this is the constant, the value that the permittivity assumes when omega tends to infinity. Now, since the permittivity does not tend to 0, we cannot apply, we cannot neglect the contribution of the integral along this semicircular path. But what we can do is we can subtract the constant epsilon infinity to the permittivity and use the Cauchy integral formula to this difference, which is holomorphic as well. So as you can see now, we have at the left-hand side epsilon of omega minus epsilon infinity, and the same occurs in the numerator of the fraction inside the integration here. Okay, now this difference tends to 0 when omega tends to infinity. So if you evaluate the contribution of the half circular part of this contour, CR, explicitly, so the integral from 0 to minus pi with respect to the angle psi of this ratio here, the fraction, times the term that comes from the differential, okay, and you consider the limit when r tends to infinity, then since the numerator of this fraction now tends to 0, you can conclude that the contribution of the half circle is negligible when its radius tends to infinity. And so in this limit, what remains is the contribution of C1 that now extends over the entire real axis. And so you get representation of the permittivity in the lower half plane, so epsilon of omega minus epsilon infinity, in terms of an integral along the entire real axis, okay? So this tells us that to know the permittivity anywhere in the lower half plane, it's sufficient to know the permittivity for real frequencies, okay? Because then you can evaluate the integral at the right-hand side and you're done. But even more importantly, what you can do with this expression is that now you can let omega, which is a point here in the lower half plane, tend to some point on the real axis itself, okay? This, of course, poses some problem in the integration along C1 because you would have a pole, there is a pole here at the point omega, which goes directly onto the integration path C1. So to avoid any problem, what you do is that you indent this integration path using a small half circle again, CA, where A is the radius of this small half circle. If you do that, you do not change the value of the integral by Cauchy theorem, and now you can let omega be a real number without any problem. Of course, now we have to evaluate this in the limit when the radius A tends to 0, okay? So we start with this expression for epsilon of omega minus epsilon infinity, where now omega is real, which is the sum of two contributions. One is the contribution from C1, which is now the entire real axis minus a small interval around the point omega, okay? Or a small interval in which the distance of the endpoints from the point omega should be equal to the radius a and not epsilon, as is written here. This is a typo, okay? And then there is the second integral, which is the integration along the half circle CA, okay? Let us see what happens when we let the radius a tend to 0. Examining separately the two integrals. If you consider the integral along C1 and you let a tend to 0, then by definition you obtain a kind of improper integral, which is known as a Cauchy principal value integral. PV stands for principal value, okay, which is an integral along the entire real axis in which you have removed a single point, which is the point omega, and you have let the interval around this single point excluded by the integration shrink to 0 symmetrically around the point omega, okay? This is the limit of the integration along C1. Whereas the integration along the half circle, CA, can be evaluated explicitly by replacing the parametric representation of the circle in place of omega prime. And if you do that, which is what is written here, and you then let the radius a tend to 0, then the resulting value is 1/2 of the numerator of this fraction, so evaluated at omega. So 1/2 of epsilon omega minus epsilon infinity, which is 1/2 of the left-hand side that you can see here. So basically, this second integral on the right-hand side tends to 1/2 of the left-hand side. So you can collect those two contributions at the left-hand side, and what remains finally is that epsilon of omega minus epsilon infinity, so the value of the permittivity at the real point omega minus epsilon infinity, is equal to a Cauchy principal value integral that involves the value of epsilon of omega prime evaluated along the entire real axis. Now it's simple to divide the real and imaginary parts of this relation simply by writing the permittivity as the sum of a real part, epsilon prime, and the negative imaginary part, epsilon double prime. If you divide the last relation in its real and imaginary parts, you get a couple of relations that are known as the Kramers-Kronig relations, and they relate basically the real and imaginary parts of the permittivity to themselves, in the sense that the real part is expressed by an integral that involves the imaginary part, and vice versa, as you can see. Those are principal value integrals, and they constitute a transform pair, actually, which is known as the Hilbert transform, and this is very well known to those who have studied signal processing. Actually, this kind of Hilbert transform applies to the Fourier transform of any causal function. So you will find it in the transverse function of any causal linear input-output system. So these are quite universal in the form. And it's useful. They are also useful in practice, because maybe you wish to evaluate you could evaluate, for example, the real part of the permittivity by measuring the absorption of the medium, which is governed by the imaginary part. So those relations are also useful in practical measurements, in addition to have, of course, theoretical value. Okay, this is the first important result that stems from causality, and whose proof has required some analytical functions technique. Let us say something more in this respect. There is a related aspect, which is the choice of the integration path for evaluating the time domain waveforms in which we are interested. Those time domain waveforms require inverse Fourier transforms. So if you know the frequency domain signal, f tilde, you should evaluate this Fourier integral. Now, if the Fourier transform f tilde tends to 0 when omega tends to infinity, which is often the case, then when the time is negative, the integration path may be closed in the lower half plane. That is because the integrand there is exponentially decreasing to 0 at infinity, using the semicircular contour that we have already seen. And the contribution of this contour vanishes as its radius tends to infinity. So, since we know that the function f is holomorphic in the lower half plane, then Cauchy theorem guarantees that the function f in time domain is equal to 0 for negative times. So causality is satisfied. Okay. So this is the converse of what we have seen before. If we know that the function is holomorphic in the lower half plane, then the function in the frequency domain, then the function in the time domain must be causal. If you instead deform the integration path in the upper half plane when time is positive, then in the upper half plane, our integrand needs not to be holomorphic, so we cannot conclude that the result is 0, and in practice it is not 0. We have a non-zero waveform in time domain. And in this case, we will find singularities in the upper half plane, for example, poles, omega p1, omega p2, and so on, and also in general branch points, so omega branch point 1, omega branch point 2, and so on. If you close your integration path at infinity using a semicircular contour in the upper half plane, and you let the radius tend to infinity, then the contribution of such semicircle will go to 0. However, you need to detour around the branch cuts if there are branch points, and you also need to take into account the contribution of poles by residue theorem. So you end up writing your time domain waveform as the contribution of all the singularities that are present in the upper half plane. In red, you can see the contribution of poles, okay, where the coefficients r, which multiply the complex exponentials, are given simply by the residues of our function f tilde at those poles. And then there is the contribution in blue that comes from the integrals around the branch cuts These are in the form of an exponential e to j omega branch point times t, which is weighted by this modulation function f of t, which comes from the integration around the branch cut. Okay, so basically we have representation of the time domain waveform in terms of pure sinusoids in red and modulated sinusoids in blue. Okay. Note that if the medium is passive, all the singularities must lie above the real axis, and otherwise you would get an exponentially increasing function of time, which is not permissible in a passive medium. So the imaginary part of all those poles and branch points must be positive, strictly positive. And as we already saw, causality then requires that your function is holomorphic, in fact, in the lower half plane. Conversely, if your medium were active, then some singularities could also lie below the real axis. This gives rise to growing sinusoids. But again, causality requires that we integrate along some line that lies below all the singularities. That is because in any case, we need to close the contour at infinity in the lower half plane to conclude that the waveform is zero when time is negative. So when you have an active medium, you should evaluate your inverse Fourier transforms not on the real axis, but on the shifted real axis, which lies below all the singularities, poles, and branch points. Okay. Okay, this concludes our introductory part of this lesson on transients. What we will now explore in the remaining part of this lesson and also in the next lesson is this one of the few analytical techniques that are available in the time domain, the so-called Cagnard-de-Hoop method. The Cagnard-de-Hoop method takes its name from Cagnard, a scientist who derived it in the 30s of last century. But actually, Cagnard himself credits Carson for having had the first idea of the method. And Carson, in turn, credits someone else, so it's not clear who was the first to invent the method. For sure, Adrianus de Hoop perfected it in the 50s and 60s of last century, so we now know the method under this name, Cagnard-de-Hoop. The motivation for this method is very simple. If you know the response of your medium to a time harmonics excitation, so you know the frequency domain solution to your wave problem, to obtain the time domain solution, what you need is to inverse Fourier transform the frequency domain solution. Okay, so for example, considering the familiar Sommerfeld half-space problem, in which you have a point source in the presence of a single planar interface between two media, we have seen last week that, for example, the reflected potential can be cast in the form of a single spectral integral with respect to the radial wave number, k rho. And this integral involves the spectral Green's function, and the complex reflection coefficient gamma, Tm, and the Bessel function J0. Okay, so this kind of spectral integral gives us the solution for the potential, for the reflected potential in the frequency domain. If you are interested in the time domain, then you should inverse Fourier transform these representations. So you end up evaluating a double integral. There is the spectral integral that gives you the Fourier, the solution in the frequency domain, and then there is the inverse Fourier transform that gives you the transient response. This latter integral can be reduced to an integration along the positive real axis of the omega plane by exploiting the symmetries that characterize the Fourier transforms of real signals. For example, the spectrum on the positive axis and the spectrum on the negative axis are related by this complex conjugate relation, since the potential in the time domain must be real. And so what you actually need to evaluate is an integral along the positive real axis in the omega plane. But in any case, you have to evaluate numerically a double integral, the integral with respect to omega and the integral with respect to k rho, and the integrand is slowly decaying and also oscillating because of the Bessel function. So this is a nasty numerical problem, which is typically computationally intensive. So if possible, it would be better to have an analytical approach rather than a numerical approach to transients. And this is what the Cagnard-de-Hoppe method provides you, because in the simplest cases, it allows you to get rid of both these integrals and to produce a solution which is expressed in a closed form. Let us see how this works, considering the simplest possible case, that is an electric line source in free space. This is a simple case because this is a two-dimensional problem. So you can see there is a line source that is an infinite line along the z-axis, which is now orthogonal to this slide. And this radiates in free space, and it is placed at the origin along the z-axis, so at the origin of the xy plane. So this is a two-dimensional problem in which there is no z-dependence. We are now in the frequency domain, and we know from elementary courses on wave theory that the potential produced by such a line source is expressed by the simplest cylindrical wave, which is the Hankel function of second kind with argument k0 rho, where rho is now the radial distance in the xy plane. So it's one of the two polar variables, rho and phi. Of course, the symmetry of the problem is such that this cylindrical wave does not depend on the azimuthal angle phi. And k0 is the free space wave number, that is the ratio between the radial frequency omega and the free space velocity c. We introduce also the reciprocal of the free space velocity, the wave slowness, we call it S0, so that k0 is the product of the radial frequency omega and the wave slowness S0, okay? This is a typical parameter used in Cagnard-de-Hoppe theory. Okay, we will for the moment ignore that we know in a closed form this cylindrical wave, and we will represent it instead in terms of a spectral integral. As we know, it is possible to do, so we represent this potential in terms of an integration performed along the extended Sommerfeld integration path, which is equivalent to the real axis. So we integrate from minus infinity to plus infinity, and what we need to integrate is the one-dimensional Green's function, this fraction here, and then there is the exponential of the inverse Fourier transform here. The integration variable being kx, okay? In the complex plane of kx, which is depicted here, the only singularities we have for this integrand are a pair of branch points at plus and minus k0, and those are introduced by ky, which is the vertical wave number, which is defined by a square root function by the separation condition. This square root function has two possible determinations, so we choose to integrate on the top Riemann sheet, which is characterized by the imaginary part of ky being negative, so that the radiation condition at infinity is satisfied. And wiggly lines in red are, as usual, the Sommerfeld branch cuts that separate this top Riemann sheet from the bottom Riemann sheet. So our Riemann surface is the union of two complex planes, the top sheet and the bottom sheet, okay? Let us see in a nutshell the essence of the Cagnard-de-Hoppe method, and then after the break we will see the details. The first step of the method consists in scaling the integration variable by introducing the radian frequency. So instead of kx, we will integrate with respect to sx. S stands for slowness, of course. The ratio between the old and new variable being the radian frequency omega. If you do that, then also the vertical wave number can be scaled in the same way, introducing the vertical slowness, Sy, which is related by a square root to the horizontal slowness, Sx. You, of course, need to change also the differential of your integral. And then you are able to write the potential in terms of an integral with respect to Sx, this new integration variable. And here I have collected the two exponentials in a unique exponential in which you can see in red the part containing the dependence on the new integration variable Sx. Note that so far the integration path remains the real axis, so it's the same as for the original kx integral. Now there is the key step, which consists in introducing a parameter tau, which is equal to the red part in the exponent I showed you before. So this red part in the exponent is now called tau, okay? So that that exponential function becomes e to minus j omega tau, which is the typical Fourier exponential that occurs in inverse temporal Fourier transforms. So we basically change variable in the integral. So we go from Sx to tau, and this again requires us to introduce this derivative in order to change the differential, okay? So we evaluate now this integral in the complex plane of tau along a certain path C in this complex plane, C tau, which is characterized by the fact that its image in the Sx plane is the real axis, okay? However, we will not actually work in this complex tau plane, but we will still remain in the complex Sx plane. What we do is that we change the integration path in the Sx plane from the real axis to some other integration path, which is called the Cagnard-de-Hope path, here in blue, which in turn is the image of the real axis in the tau plane. That is because we are interested in transforming our integral in an inverse Fourier transform in a direct Fourier transform with respect to time. So we need to integrate along the real axis of this parameter tau. Actually, we will not integrate along the entire real axis of the tau complex plane. That is because by causality, our signal will not arrive before the time that it takes for the wave to go from the source to the observer. Now, this time is equal to the space between the source and observer, so the radial distance rho, divided by the free space velocity, which is the same as the product of rho times the wave slowness, S0, okay? So there will be nothing before this wavefront arrival time, and so we will integrate in tau from this specific arrival time up to plus infinity. Okay, we wish to integrate in the Sx plane along the Cagnard-de-Hope path, which is the image of this orange portion of the real axis in the tau plane. Okay, if we are able to do that, then basically we will have managed to transform our original integral into an integral which runs along the real axis in the tau plane, which has the form of a direct temporal Fourier transform. Now, if you are at this point, what you can see here is that your frequency domain potential at the left-hand side is written as if the Fourier transform of some function f of tau, whose expression is given here at the center. And then by inspection, you can conclude that the inverse Fourier transform of the left-hand side must be the function f, okay, f of t, of course, multiplied by the unit step function, the so-called Heaviside unit step function. That is because your integration limits go from this time here, the wavefront arrival time, S0 rho, to plus infinity. Okay, so our potential will be 0 before the wavefront arrival time, and this is what the Heaviside unit step function tells us. And after that time, it will be equal to the function f of t, which is obtained analytically, so in a closed form, as you can see from its expression here at the center. This is the method in a nutshell, but now we will see explicitly all the steps for the specific example we are considering now after a 10 minutes break. Okay? So see you in 10 minutes. Okay, here I am again. Can you hear me?
Yes.
Okay. Okay, so basically, as we have seen, this Cagnard-Hopf method saves you from the need of performing a double integration, because it starts with an integral representation of the frequency domain waveform and transforms this single integral, which is a spectral integral, into a time domain integral with respect to this new time variable tau. And in terms of this new variable tau, you at the end find this time interval, which is a Fourier transform, a direct Fourier transform. So by inspection, you are able to evaluate the transient version of the potential by looking at the integrand itself, which is available in a closed form. The key step is the change of variable that introduces this time variable tau. And in the specific example we are considering, this time variable tau is expressed in terms of the old integration variable Sx. In this way, it's Sx times x plus Sy times the absolute value of y. This comes from the form of the original integrand, that is explicitly this one, in which we have collected in a single exponential everything, and in the exponent, what multiplies minus j omega is what we will call tau, okay? So we will now explore a little bit closer this relation between the new variable tau and the old variable Sx, which is explicitly given by tau is equal to Sx times x plus absolute value of y times the square root of S0 squared minus Sx squared. This relation can be inverted, and you can express so both Sx and Sy in terms of the new variable tau. And this is useful because then you can deduce the image of the interval of the real axis between the wavefront arrival time S0 rho and plus infinity in the tau plane in the image of this interval in the Sx plane. So you can do an exercise by yourself. You can invert the relation here between the two variables tau and Sx, and so express, for example, Sx in terms of tau. The result is this one, in which you can see tau now is at the right-hand side, okay? And it is also inside this square root here, which has two determinations. So this is why you have a double sign here. The same is true for the vertical slowness as y, which is expressed as a function of tau by this right-hand side. And again, we have two determinations. The two determinations are the two possible choices of the signs in front of the square root. And this corresponds to the two parts of this blue integration path, which is actually a hyperbola. And you can see that this hyperbola is the image in the Sx plane of the real axis in the tau plane, in particular of the portion of the real axis that goes from the wavefront arrival time S0 rho to plus infinity, okay? There are two portions of this hyperbola. One portion is this blue solid line in the first quadrant of the Sx plane, and this goes from this purple point here, S0 cosine phi, to infinity, approaching this linear asymptote. And then there is also the dashed blue line, which goes in the fourth quadrant asymptotically to the other asymptote of the hyperbola. And this instead is in the bottom Riemann sheet. This is why the reason why I have represented it with a dashed line, since we have crossed this branch cut at this purple point, okay? So if you let the time parameter tau go from S0 rho to plus infinity, if you choose the upper signs here, then you will run onto the upper part of the hyperbola. If you choose the lower signs, you will be on the bottom Riemann sheet, and you will run in the dashed bottom part of the hyperbola. Okay? So what we will do in the x-axis plane is that we will change the integration path from the original orange one, which is equivalent to the real axis, to this blue path, which is by definition the Cagnard-de-Hope path, which, note now, is oriented upwards, so that it is equivalent to the real axis. As usual, the equivalence can be shown by joining those two paths through semicircular arcs, then letting the radius of the arc go to infinity, and then proving that the contribution of those arcs tends to 0 when the radius tends to infinity. So it's quite standard to show that the integral along the original orange path is equal to the integral along the Cagnard-de-Hope path. But why should we wish to integrate along the Cagnard-de-Hope path? Because by definition, the latter path is the image of the interval on the real axis in the tau plane that goes from S0 rho to plus infinity. So you can write this integral by parameterizing it with the new variable tau as this kind of integral, which is, of course, a standard temporal Fourier integral, okay? In which you can see, however, since we integrate from S0 rho to plus infinity, we would actually integrate only on the upper portion of the Cagnard-de-Hope path. To take into account also the lower portion, we have written the integrand as the difference between the integrand evaluated on the top part of the Cagnard-de-Hope path and the integrand evaluated on the bottom part, the dashed line. Okay, the difference, why the difference? Because as you can see here, we are going upwards on both the bottom and top parts. However, the bottom part was oriented downwards. Okay, so if you change the orientation, then you should also introduce a minus sign, and that is why here you have this folded integrand, which is the difference between the value on the top and on the bottom parts of the Cagnard-de-Hope path. We are now able to evaluate this red part of the integrand explicitly. This just requires for us to do a differentiation of Sx with respect to tau. If you do that, then you will discover that this difference between the top and bottom parts of the quantity in square brackets is equal to 2j divided by the square root of tau squared minus S0 rho squared. If you introduce this into the integral with respect to tau, you get this result that is a Fourier transform, a direct Fourier transform. And so you can read by inspection the time domain potential simply by looking at what's inside the integral, except, of course, from the Fourier exponential. What's inside the integral is 1 divided by 2 pi, and divided by also the square root of tau squared minus S0 rho squared. This is our temporal waveform. However, this waveform is valid only after the wavefront arrival time, S0 rho, and this is why we introduce this Heaviside unit step function, which reflects the fact that this Fourier integral is not going from minus infinity to plus infinity, but from S0 rho to plus infinity, as causality requires. Okay, so we have managed to evaluate the time domain potential produced by a line source in free space by this clever change of variables and of integration path in the complex plane, which is known as the Cagnard-de-Hope method. The validity and the usefulness of the method, of course, is not only related to free space problems, for which we would be able anyway to find the solution by different means, but in particular to problems in layered media. And in particular, we will examine the method when our line source now radiates in the presence of a single planar interface. So again, the Sommerfeld problem now with a line source instead of a point source. Let us assume that this line source radiates in the presence of a half-space filled with an ideal dielectric medium, so it's lossless and non-dispersive. Those are important assumptions that make the Cagnard-de-Hope method applicable. And let us examine, for example, the reflected potential, just for definiteness, because it would be simple to examine also the transmitted potential. But let us stick to the reflected potential, so we will work in the upper half space where y is positive. As we have seen, we have this spectral representation of the reflected potential in the frequency domain, which involves the reflection coefficient, which is now a TE reflection coefficient because of the polarization of the field produced by this electric line source. As usual, you can see the vertical wave number ky1, which is related to the integration variable kx by the usual square root that comes from the separation condition. Now, since we have a reflection coefficient, this introduces two pairs of branch points associated with the vertical wave numbers in air, k1 minus k1, and in the dielectric medium, k2 and minus k2, with the associated Sommerfeld branch cuts, those wiggly lines, that for clarity have been drawn a little bit shifted from the real and imaginary axis, but you should imagine that those lines run exactly along those axes. And in addition, there would be also poles. However, it can be shown that the TE poles are on the bottom Riemann sheets, and they do not enter in this formulation. So we don't need to take care of poles. Since we are assuming that the line is in vacuum, so the wave number in medium 1 is smaller than the wave number in medium 2, or which is equivalent. The wave velocity S1 is larger than S2. This is a typo, of course. The sign should be reversed. That is, the source resides in the medium which is optically less dense. Okay. Then the situation of the branch points is exactly as in this figure. Okay. And what we do is that we enforce the change of variables typical of the Cagnard-de-Hope method. So our first step will be to scale the integration variable, changing it from kx to sx, the scaling factor being the radiant frequency, so that our frequency domain potential is written in terms of this integral with respect to sx, in which we have highlighted in blue the reflection coefficient, and in red, as we did in the previous example, the coefficient that multiplies the radiant frequency in the exponent of this exponential function. Now we introduce the parameter tau, which is given exactly by this red coefficient here, which is a function of the integration variable sx. And again, we are able to invert the relation between tau and sx, so to express sx as a function of tau, and also the vertical wave number in the vacuum, sy1, again as a function of tau. Consider that we have written these expressions in terms of polar variables, rho prime and phi prime, which are now defined with reference to the so-called image source, that is the geometrical image of the source location, which lies inside the dielectric region at the abscissa minus y prime. So you can see rho prime is the distance between the observation point and this image source, and phi prime is the angle formed by this line with the horizontal axis. Okay, introducing these polar variables is useful in order to write compactly the equations and also to interpret them, as we will see. Once we have introduced this parameter, then we change the integration path from the original orange one to the Cagnard-de-Hope path, and this is exactly the same path we have already discussed with reference to the free space case. The only difference is now in the integrand, which now involves also the reflection coefficient, because here we have an interface, so we need to introduce also the reflection coefficient, but everything else is the same. So basically we end up with an integral with respect to the real parameter tau that goes from S0 rho, the wavefront arrival time, to plus infinity. And we have the Fourier exponential, e2 minus j omega tau. And everything else is these square brackets, that is the difference between the top and bottom parts of the Cagnard-de-Hope path of this red part that was already present in free space and the blue part that comes from the presence of the interface, okay? So we again try to evaluate analytically this square bracket here. The part that is also present in free space has already been evaluated, and that's equal to plus or minus 1 divided by the square root of tau squared minus S0 rho squared, okay? And those plus and minus characterize the top and bottom values of this term here, whereas the reflection coefficient can be easily shown to have the property that its value on the top part of the Cagnard-de-Hope path is equal to the conjugate of its value on the bottom part. So when you evaluate the difference, in order to evaluate this folded square bracketed function here, what remains inside the integrand is a fraction in which the numerator is given by the real part of the reflection coefficient evaluated on the top part only of the Cagnard-de-Hope path, the blue part here, and the denominator is the square root that was already present in free space. So again, we have arrived at the final step in which we recognize that this is a direct Fourier transform, and therefore we write by inspection the time domain waveform, which is now exactly the same as in free space, but now in the numerator we also have this additional blue term that incorporates the reflection coefficient of the interface, which is to be evaluated on the top part of the Cagnard-de-Hope path, okay? And so it is implicitly a function of time, tau, okay? Now here tau should be more correctly be t, since t is the time variable that we are using inside the argument of the function at the left-hand side, okay? Something similar but not exactly equal is done in the case when the source is placed in the optically denser medium. So now assume that your source is located inside the dielectric, which is now medium 1, and vacuum is instead medium 2, okay? Now in this case, the situation is opposite in the complex plane because now K1 is larger than K2, okay? So S1 is larger than S2. So the medium 1 has a wave velocity which is smaller than S2. Again, this sign should be reversed, okay? And as a slowness, sorry, that S is a slowness, it's not a velocity, so this sign is correct. The wave in medium 1 is slower than a wave in medium 2, so S1 is larger than S2. What's the difference in the procedure? Well, if you wish, if you evaluate the first step of the Cagnard-de-Hope method, then everything is the same. You scale the integration variable introducing the radian frequency omega, and also you introduce the same time parameter tau, which depends on Sx in the usual way. So you need to write your frequency domain potential as an integral along the Cagnard-de-Hope path. However, we now should distinguish between two cases. In the first case, your observation point lies inside this triangle whose sides are the vertical segment from the source to its image, and those two red segments, which are defined by the critical angle for refraction, okay? So the angle above which you get total internal reflection. If your observation point is like in this figure, then you can see that the angle phi prime will be larger than the complement of the critical angle. And in turn, this means that the apex of the hyperbola, so the point S1 cosine phi prime here, will be located on the left of S2. So everything proceeds as we have already discussed. This is the Cagnard-de-Hope path, and so you obtain the evaluation of the time domain waveform exactly as before. However, there is another case, the case when your point is outside that triangle. So in this case, the angle phi prime is less than the complement of the critical angle. Now in this case, S1 cosine of phi prime is larger than S2. So as you can see, your hyperbola is located on the right of the branch point S2. So this means that you cannot deform the original integration path directly onto the Cagnard-de-Hope path, that is onto the hyperbolic path. This is because you would sweep across a branch point, the branch point S2, which is not permissible, because in this case you could not employ the Cauchy theorem to prove the equivalence of the two integrations. What you need to do is to integrate around this additional portion that is formed by two horizontal segments that have been drawn for clarity displaced, but would be actually both on the real axis of the SX plane, which lie partly on the bottom sheet here, the dashed portion, and partly on the top sheet. So they are both on the real axis, partly on the bottom real axis, and partly on the top real axis. So in this way, you can show that the original integral along the orange path is equivalent to the new integral, which runs along the hyperbola in the bottom Riemann sheet, then this horizontal segment again on the bottom Riemann sheet. Then you turn around the branch point S2, you go then to the top Riemann sheet, you run along this horizontal segment on the real axis, and finally on the top part of the hyperbolic Cagnard-de-Hope path in the first quadrant. Okay, it is quite simple to show that when Sx is equal to the branch point S2, that is, you are here, then the time parameter tau is equal to this specific value, tau over bar, which is equal to this expression, okay, given here. Whereas when you are on the apex of your hyperbola here at S1 cosine phi prime, then you are at a different time parameter tau, which is larger than the previous one, and that's equal to S1 rho prime, okay? What's the difference then in the evaluation of the time domain waveform? Well, you have the contribution not only of the hyperbola, but also of the horizontal part of the integration path. As before, you can write the tau integral as an integral along the real axis that goes now from tau over bar to plus infinity. Now, if time is less than S1 rho prime, then the quantity here in red can be shown to be purely real, whereas the reflection coefficient can be shown to be the complex conjugate of each other if you are above and below the real SX axis. So we are considering the contribution of this portion here. And now, since SY2, and this is because SY2 is on two different Riemann sheets. So when we are evaluating the potential for times less than S1 rho prime, then the square brackets inside the integral takes this specific value that is written here, and it's also the time domain waveform for those value of time. Okay, we see that in the numerator there is the imaginary part of the reflection coefficient. If instead time is larger than S1 rho prime, then the quantity in red would be purely imaginary. So in this case, what emerges is the real part of the reflection coefficient. So if you collect those two results, you end up with the complete time domain waveform, where now you have two different expressions. The one above, which involves the imaginary part of the reflection coefficient, holds for times between tau over bar and S1 rho prime. as you can see, there is a difference of Heaviside functions. This difference is different from 0 only for times between tau over bar and S1 rho prime. Before tau over bar, by causality, we don't have anything, so it's the waveform is identically 0. After S1 rho prime, we have this second expression here at the bottom, in which you have the real part of the reflection coefficient, always evaluated on the Cagnard-de-Hope path. So the situation is more complex, and the complexity comes from this additional term here that would not be present if we were in the previous situation, that is, if the source were in the less dense medium. These additional terms is related to the head wave, and that's why that's easy to see that, because now the wave in region 2 at the bottom is faster than the wave in region 1. So if you consider the path that we know is followed by the lateral wave, also called the head wave, then it's easy to see that the time it takes to follow this red path that is partially inside the dielectric with this angle, this critical angle here, theta c, then this runs partly at grazing along the interface with the velocity of the lower medium, and then again inside the dielectric medium, again forming this critical angle. Well, the time that it takes for the head wave to cover this path in red, this is exactly equal to the time tau over bar, which is in this case the wavefront arrival time. So it's the first arrival to the observer. That's why we call the lateral wave the head wave. That's because it's the first thing that arrives to the observer. So it's faster than the reflected wave. The reflected wave goes through the path in blue here. So the arrival time of the reflected wave is given by rho prime times S1, and this is larger than the arrival time of the head wave. Okay, so we have seen that the Cagnard-de-Hope path naturally introduces the concept of a head wave, and the head wave originates, as we already saw last week, from the presence of a branch point. In this case, the branch point associated with the medium where the wave is faster, so the lower medium, that is vacuum in this case. Okay. Okay, this concludes our lesson for today. What I have discussed today is more or less contained in a chapter of this very well done book by Professor Chu, Waves and Fields in Inhomogeneous Media. It's a classical book about time harmonic but also transient waves in inhomogeneous media. To finish, I would like to introduce to the final assignment associated with this course. This is, of course, only for those who are attending this course as a formal part of the PhD program. So, since we are required to assign a specific formal task to students in order to let them gain their credits, in this case, the 6 credits associated with this course, then the assignment is to read a paper, which is this paper by Leopold Felsen, which was published in 1986 on the Journal of Optical Society of America, Part 1. The title is, as you can see, Real Spectra, Complex Spectra, Compact Spectra. And this is a beautiful paper written by one of the most important experts of waves that have been that have appeared in the last century, this Professor Felsen. And basically, this paper is an overview of how, using complex variable techniques, you can achieve compact representations of wave phenomena, which would otherwise be much more complicated to describe if you remained confined on the real axis. So if you, instead of using a complex spectra, you would use a purely real spectra. The assignment is to read a specific section of this paper, section 2A. So it's a small portion of the paper, which anyway is not a long paper, but it's dense. And to prepare view graphs in PowerPoint that illustrate the contents of this section only, and then present the view graphs to me, probably at distance if the situation goes on like now, but you can do that at any time. So once you have some time to do that and it's convenient for you, you email me and we can get an appointment and discuss these either at a distance or hopefully in presence sometime in the future. Okay. That's all for today.
Is it free access?
The paper is not free access. Thanks for the question. I was forgetting to say that the paper has been posted on the e-learning site of this course, so you can download it from there. Okay. Okay. So that's all. Now I will post these slides in the e-learning website as well, and in a few minutes also the recording of this lesson should be available in the usual shared folder of Google Drive. Okay, so thank you again for your attention.
Thank you.
And see you next Thursday when there will be also a whole program. There will be a colleague of mine who will give a seminar. So my lesson will be shorter than usual. I will probably confine the time of my lesson to 1 hour or even less, and then the second hour will be given by my colleague Dr. Fuscaldo, who will give you a seminar on some hot topics related to the contents of this course. See you on Thursday then.
Thank you. Bye.
Bye-bye.